Matt's invited.
in the rain.
Yeah, it's like, yeah, the attendance in my 4190 class is falling off a little bit, and it's really disappointing because I'm fixing to get them some Rubik's cubes. We'll see if that brings them in. Jared, let me answer your question before we so let me give you a couple of examples to show. He was asking about, we have the theorem that said that the order of the Galois group divides the Euler free function. His question is, let me give you a couple of examples.
Yeah, it's like, does he fall when the quotient field is?
Actually, I'm going to use the same polygon on a couple of different examples. And this is a bit of silliness that can occur. So suppose you have the field, your starting field Z2, and you look, and your polynomial is x to the 12th minus 1. Well, mod 2, x to the 12th minus 1 is x cubed minus 1 to the 4th. Right? So we have, which is actually, let's take this down a little bit further. This is x minus 1 to the 4th. Right. Times so we have the splitting field. Right. So the Euler phi function, well, is 2, let's see, this is, better write it out, 2 squared times 3, which is 2 to the 1 times 1 times 2 is 4. But of course, the degree of the extension here is just 2, right? So here, the degree of the extension, cyclotomic extension, you really would just get this. Now you might think, well, Jim, that example is a cheat because after all, you took advantage of the fact that this characteristic too. And let now again, the Euler phi function here, 4, but the cyclotomic extension you ain't going no further than the complex numbers there, right? So here the extension degree is 2, and it strictly divides the. In fact, with this second example, you can just go bananas, right? Because you can have arbitrarily large things, but you know, going to a cyclotomic extension is only going to be at most degree 2, because once you hit the complex numbers, you're algebraically closed. Okay, any questions? Okay, so recall that R inside T are, I think I said domains at this point. You can do this in terms of range as well. Oh, by the way, I've pretty much decided there's going to be one more homework. I will give it to you sometime this week, and it'll probably be due during finals week sometime. Right, so you have just finish up. And I hate to break this to you, but for our final exam, we're supposed to get together, and I'll probably yammer a little bit more about range or whatever. So during exam time, we'll all get together and I talk about magical algebra.
Is that going to be
the Monday, Wednesday, Friday during the exam week, or just during when we would have had our final?
It would be just during when we had our final, because they moved the rooms around, so if we try to do it at this time, who knows what we're gonna get.
Do you know which date that is?
I'll let you know, it's Thursday, I think.
I'm 97%.
Yeah,
You're right, I bet you're right.
Because my
because-
students have an exam.
Yeah, because I'm so used to, always teaching 8 and 9, and this is the only semester I taught 9 and 10, so this is a 10 block, maybe it is Tuesday.
I think it's Tuesday at 3.
Yeah, 3 to
3 to
5:30.
Wow, what a wonderful way to spend the afternoon. Yeah, do you have a conflict?
No, my students have an exam they're asking. That's why I know what it is.
Yeah, but doesn't that make a conflict for you, or?
No, it's at the next section.
Oh, okay, gotcha. So T is integral over R, if T is a root of a, and this is important, monic, and actually we'll see this in the proof, or in the polynomial. F dash equal x n, a n minus 1, x n minus 1. 0 and Rx. And last time we showed that every element of Z is joined with the square root of -5 is integral over Z. However, the only elements of Q that are integral over Z are the elements that are integral over Z themselves, or I'm sorry, the elements of Z themselves. Okay, I'll get to that example later. Here is, I call this a lemma. I really shouldn't, because it's much more robust than lemma, but keeping an indentation I've got there. Let R and T be domains. By the way, let me point out again that, do you remember back in 85, this is 85, do you remember earlier, we talked about algebraic elements, and I said, well, it's not clear that if I have this element alpha that's a root of some polynomial over a field, this element beta that's a root of some other polynomial over the same field, that the sum of those will be the root of a perhaps third polynomial, right? That wasn't clear at all, right? And here I think it's even shaky. Right? Is it clear that if you have a root of a polynomial and then some other root of some different g of x, then the sums and the products are still going to be roots of polynomials? Surprisingly, they are, right? Otherwise, I wouldn't be talking about this crap. And monic is very important. And this lemma is going to help us get to the heart of that. One, U is integral over R. That is the root of the polynomial equation. Number 2, there exists a finitely generated R module A, our submodule such that this is amazing, right? I mean, what's this really got to do with you satisfying, or that is you being a root of some monic polynomial equation? Equivalently, there's some finally generated subpiece of T, finitely generated is important, that acts like a vacuum cleaner on you. It sucks it back in. This is, I mean, what's one thing got to do with the other? And maybe an auxiliary question after that is, why would you care, right? And hopefully I'm going to answer both of these. And the proof of one direction is really a slick linear algebra. It's really a nice application of linear algebra. Let's do a suppose U is the root of polynomial xn plus rn minus 1, c minus 1. Let A be the R mod generated by 1 U Q squared. Is it clear why this works? Maybe not. So when I say, notice that this is the module just generated by these finitely many things, right? So everything's an R linear combination of these things, right? And of course, that's obviously it's contained in T because U is contained in T, so your power is. Okay, why does it work, right? Well, we need to show that UA, okay, well, so let well, actually, that's my choice here. Let's let A be S n minus 1, A n minus, or U n minus 1. That's S n minus 2, U n minus 2. That's 1 U, that's S0, with all the SIs and R. So that's a typical element of what this looks like. Now, look at a U. Almost in a Newman, right? How do I, this one UN is killing it, right? Can we fix it? Well, notice that UN is minus Rn minus 1, UN minus 1, minus R1 U minus R0. So I can replace this by Sn minus 1 minus Rn minus 1, Un minus 1 minus R1 U minus R0 plus Sn minus 2, Un minus 1 plus 1. Now this is in A. Right, because notice this is now an R linear combination and everything has powers n minus 1 or less. Everybody okay with that? Now suppose for some greater than or equal to 1, U to the K, A is contained in A. And the induction is easy. Well, U to the K plus 1, A is U times U to the KA, and this is in A by induction. And so now refer back to basics, because we just did this computation. So if U is integral, we found it's basically just the low powers up to n minus one, where n is the degree of the polynomial. Everybody cool so far? The cool part of this theorem, of course, is that it works in the other way. That is, if you find a finitely generated module that vacuum cleaners in and sucks it in, wow, that element is integral. All right. So let's look at that. So let's suppose we have, yes.
I don't really understand why we had to do the induction piece in this first part. Like, I don't understand. Yeah, I don't understand.
Oh,
why we had to do
yeah,
this
I
first.
guess actually, yeah, I got too excited, yeah, because really all we did is show that UA is an A, that's all we need. Yeah, I was so focused on the powers of A that I just deducted on it. So by induction, I proved that all powers work, but you don't need it, that's all you need. You're absolutely right.
Okay.
Absolutely, that's all you need. Yeah,
I
I
was
do
like,
this.
I was looking at the board,
Like,
I was
I
like, maybe,
understand.
because it's.
But I
Yeah,
don't know
whenever you
why.
see
But I was
like
like,
that,
I
you
don't
should-
know.
You should like shoot me with one of those tranquilizer darts, like the Black Kingdom or something. Yeah, I just got all carried away. I was like, oh, this is anyway, so
We're all confused.
here's the cool part. Suppose we have an R submodule T, call it A. It's finally generated. So I'll say that it's generated by, let's say, now, what we know is, I'm going to take advantage of this. We know that UA is contained in A. Correct. And so when I multiply U times any AI, it has to be a linear combination of these AIs, right? Because AI is in this module. So when I hit AI by U, it has to be a linear combination of these generators, right? And so where the lambdas, of course, are in R. I agree with that. So you go through all your AIs. A1 is some lambda, 1J, AJ, and A2 is J equals 1 to N, lambda 2J, AJ, so forth and so on. Right? Quite cool, man. So if you look at this what this means is right. So let me write this. Right. Check myself here. Make sure I didn't transpose this or something. 1, 2. Yeah, that looks right. I think I got that right. Anyway, so what this means is U is an eigenvalue. And so take the determinant of that, of course, what you get is a polynomial, right? And this here is a monic polynomial. Yeah, that's really kind of cool, isn't it? So here is a theorem that follows from this. Right. So here's a theorem that follows from this. What are inside TV domains? By the way, this also works for rooms of zero divisors, but there's a special annihilator condition that you have to put in there, and it's more technical than I want to mess with right now. It's not too bad actually, but if you figure integral over R, then so R so here's the first part of this is why we would care for it. Because the previous lemma allows us to do this. Remember, if you just take the definition of integrality in the sense that U and V are roots of some monic polynomial with coefficients in R, it's not really clear what the U plus V and UV are also roots of some other monic polynomial. And it's certainly not clear what the polynomial should be. However, if you take the characterization from our previous lemma, it's not so bad, right? So let's put A and B be finitely generated. Our modules such that and VB. Right? The integrality of those guarantees their existence. So it's not. If A is generated by A1 up to AN and B is generated by B1 up to BM, then AB is generated by all possible products. So there's MN generators, right? And if you look, A plus B times AB is contained in there because every generator in this is a little AI times a little BI. And the little AI, what am I doing? There we go. Sorry about that. That's U plus B. Every little AI absorbs the U and every little BI absorbs the B. So you're still in there. And also UV. And there you go. Let me make sure that a typical generator of AB looks like that. So notice that when you multiply this through, then U is absorbed in the AIs, so it's still an AB. And B is absorbed in the BJs, so it's still in here. So that's why that works. And the product, I think, is a little bit easier to see. So sums and products of integral elements are integral, so it forms a subring. If R and T are domains, then this is called the closure of R in T. So the sub means where you're living, and the little hat, little overline means that it's a closure. This is the set of stuff in T such that Z is integral over R. Is a subring. Notice, of course, that every element of R, well, since this is containment, every element of R is contained inside of T, so it's in T, and every element of R is integral over itself because it's a root of the polynomial x minus R. So let me give you some terminology here. Any questions? By the way, the corollary needs almost no proof because we know that sums and products are there, so we're good to go. Here's some terminology, definition. So I've already mentioned that the integral closure of R and T. If the integral closure of R and T is equal to R, we say R is integrally closed. That is to say, if the integral closure of R and T, you don't get anything new, right? You only get the trivial elements of R themselves in there. Then we say that R is integrally closed to T. T is the quotient field. Of R. Then and sometimes we write just R bar. So if you ever see R bar just by itself with a subscript, that means the integral closure is quotient field. If R bar equals R, we say R is integrally closed. Okay, so we had an example of a ring that was integrally closed last time. I'm going to do something a little bit more general in a moment. But let me make the statement that if you have a ring that's integrally closed, when I first started really getting more serious, this is one of the aspects of commutative algebra that I really like, because I mean, basically you're talking about roots of polynomials, which is where most of us kind of started out. Rings being integrally closed, there are lots and lots of theorems there that tend to sometimes fall apart when they're not. Having all the roots of the quotient field that are roots of polynomials already in there is a condition that is stronger than you would think it is just first seeing it, right? But there's zillions of theorems that, if you're integrally closed, you have this, and when you're not integrally closed, sometimes weird things can happen. So let me give you some positive results. I'm not going to prove this first one, a little bit more machinery, and we may come back to it later. By the way, this is often an indicator that a property is good, strong. Yeah. Or is integrally closed. And so Rx so any ring that's integrally closed, its polynomial ring shares this property. I will prove this one. And this generalizes our example from last time. Factorization of by the way, this isn't as general as possible either, but I'm not going to get too far in the weeds. But has anybody ever heard of a GCD domain? See if you can guess what a GCD domain is. Any two non-zero elements have a GCD, right? The GCD domains are also integrally closed. Let's prove this for unique factorization domains. So suppose you start with your favorite UFD, quotient field K. And this proof is going to, I hope you don't think I'm wasting your time too much, because this proof's going to look almost exactly like the example I did. Okay, take an element of the quotient field, call it A over B, and just so we can make our proof a little more streamlined, let's assume that we produce the fraction, right? So there's no common factor between A and B. And suppose A over B is integral over R. So this means that A over B n plus R n minus 1, A over B n minus 1, R1 A over B, R0 is 0. And so this means that AN and just clearing the denominators there. Now suppose there exists P, a non-zero PNR, a non-zero prime such that P divides B. Well, of course, P divides 0 there. And if P divides this mess, then P divides A n, which implies P divides A as P. But GCD of AB equals 1, so no prime divides and if no prime divides B, then we R plus A over B is in. So any integral element of the fraction field is already in. Okay, questions on that? Okay, I'm almost embarrassed to write this next one down. It's very easy to prove. But surprisingly, I record this because even though it is kind of silly, we will find it useful on a couple of occasions. Lemma. R inside TB domains and U when R inside TB domains and U a unit of T, then U inverse T if and only if U inverse R plus U. So, oh, okay, I got your point. Yes. That's correct. Intervals are typo. Yeah, I got that right in my notes. I just flipped out. Okay, U inverse is interval over R if only if U inverse is in R U, R adjoint U. And remember what this is this is a small string that contains both R and U, so it looks like polynomials, if you will, in U. Fast and loose a little bit. The proof of this is, like I said, not very difficult. Let's suppose U inverse over R. What this means is U inverse N plus Rn minus 1, U inverse N minus 1, or 1 U inverse plus R0 and 0. Now, what I want to do here is multiply by U to the N minus 1 power, I guess. And that's going to leave me with U minus 1. And let's see, that's going to be U to the 0. U 1, 1, U to the N minus 2, plus R0, U to the N minus 1. So U inverse is minus Rn minus 1 plus Rn minus 2 to U plus R0 U N minus 1, which is in Rn. And the other implication is just almost a reverse of this. If U inverse is in RU, then U inverse is equal to negative Rn minus 1 U minus Rn minus 2 U minus R1 U to the N minus 2 minus R0 U to the N minus 1. That's what it means for U inverse to be in RU. Multiply by U to the 1 minus N to get U inverse equation of integrality. So it's almost a complete reverse of the previous. Okay. Any questions? Okay. Let me give you a last little ditty before I give you something that'll be useful in the next section, because we're going to look at integrality from the point of view of valuations, which is kind of a really cool way to look at it. Lemma. I will be using this one later as well. An intersection of integrally closed domains Okay. So this is kind of cool. So if you take a bunch of integrally closed domains and you intersect them, then it's going to be integrally closed. So in particular, so for example, if you have a bunch of UFDs and you intersect them, all the UFDs are integrally closed. The intersection, I don't guarantee it's UFD, but it will be integrally closed. All right. Proof. You can close. R let R be the intersection of all these closed domains. Let alpha be an element of the quotient field of R. And suppose alpha is a root of x, which is x n, oh sorry, n minus 1, 0. Suppose alpha is a root of some monic polynomial coefficients of R. Let me point out that if it's got coefficients in R, it's got coefficients in Rix. And if alpha is in the quotient field of R, then it's certainly in the perhaps bigger quotient field Rix. So alpha is in Ri for all I. Because each I is integrally closed. Alpha is an element of the quotient field of R, therefore the quotient field of Ri, that's the root of this polynomial. Since it's the root of this polynomial, it must be in Ri for all I, therefore alpha is in R. Because it's in every one of these Ri's. Okay, any questions? So I'm going to start talking about valuation domains here. So I'm going to start you kind of with a teaser here. And here is my teaser. I remember when I first encountered in my travels valuation domains, and I thought, how difficult could this possibly be? How many of you have ever heard of valuations before? It's something like a measure of size on a field, right? It's like an absolute value in a certain sense. That's real fast to list. Tell you what a valuation is next time. But a valuation domain is something like this. Suppose I have an integral domain that has the following property. If I pick two elements out of it at random that are non-zero, one of those elements divides the other. I remember the first time I saw this definition, like, how hard can this be, right? I mean, I can give you an example, a field, right? I mean, in fact, field works both ways, because given two non-zero, they both divide each other. But I mean, I thought, these guys, I mean, look, even for the integers, which is everybody's favorite prototype of ring, this is wildly untrue, right? 2 and 3, neither one of those divide together. These things can be amazingly complicated, believe it or not. And in fact, I can build a valuation domain for you where I can stack, well, there's a field, so I've only got the zero ideal. I can have exactly the zero ideal and a maximal ideal, you build it that way, and I can make that one either Noetherian or non-Noetherian. I can stack the prime ideals higher, but if I stack them higher than just that, they always have to be non-Noetherian. Well, I can make them two-dimensional, three-dimensional. I can make them infinite dimensional. And in fact, I can make them so big that there is no height one prime. So what I mean is, you have the zero ideal. If you have any prime ideal, there's always another one down there, and always another one in between. So even though this looks like a very easy thing, pick any two elements, one of them divides the other, these have an incredibly rich structure on them. And in fact, it turns out, so this is a little bit of a spoiler, these are related very much to integrally closed domains, because one of the big theorems that we will see is if you have any integral domain, its integral closure. So you take all the integral elements in this closure field will be the intersection of all the valuation domains that contain it. So, and that's actually very useful. We will get to that later. Any questions here or there? All right. Well, you all have a good one, and we will catch you on Wednesday.